Hello, we're going to do a very little short video here on section 5.3 on Hamiltonian graphs. Okay, the name Hamiltonian comes from Sir William Rowan Hamilton. He's an Irish mathematician, famous for many other things. As a matter of fact, if you look on the Wikipedia page for him, I don't even think they mention the graph theory information. Okay. So let's make a few definitions here. We're looking at Hamilton graphs or Hamiltonian path, excuse me. Okay. A Hamiltonian path is a path between two vertices that it passes through all the vertices, excuse me. Hamiltonian path is a path between two vertices in a graph if it passes through each vertex exactly once. Okay, so we had Euler path in the previous video. An Euler path was one between two vertices that passed over every edge exactly once, but Hamilton path has to go through every vertex exactly once. And next to Hamilton, we don't want circuit, we want cycle. Okay, if you go back and look at, there's a difference between a circuit and a cycle. And a Hamilton cycle is just basically a closed Hamilton path. Okay, so it is a closed path passing through each vertex exactly once. Okay. Now the book adds the restriction that a Hamilton cycle passes through each vertex. It's a closed path passing through each vertex exactly once with distinct edges, but I don't think that's necessary. If you pass through each vertex exactly once, you're certainly not going to go over an edge twice. So I don't know why the book adds that caveat there. Other books on graph theory don't. And a Hamiltonian graph is one which possesses a Hamilton cycle. Okay. Okay. Now, Hamilton originally looked at this. There was a game called Around the World, and the idea was you had this dodecahedron, which I've got pictured here, and it was sort of a globe, and at each vertex of the dodecahedron there was a location on the Earth corresponding to that vertex, and the idea was, can you make a trip around the world hitting each vertex, but never each vertex exactly once. Okay, and so people would pass this around as like a party game and try to come up with a way of doing that. Now, if you take, ooh, that's too big. If you take the dodecahedron and flatten it out, then you get this graph here on the right, in the middle. Okay, and so can you find a Hamilton path on this graph would correspond to a cycle going around the dodecahedron? And yeah, there is one. Let's start here. Now we want a cycle, so I want to come back where I started. So let's go here to there, and there are others. Then not just the one I'm going to do here to this thing. Now let's go inside to this vertex, then to this vertex, then to this one, this one, this one, this one, and this one. Now inside again, 2, 3, 4, 5, oops, I missed 6, 7, 8. So there is your Hamilton cycle for the dodecahedron graph. Now the graph I have over here on the right is what's called a Herschel graph, and it's not Hamiltonian. And you're welcome to try to spend some time trying to come up with that. Okay. The bottom graph I have here is a complete graph. This is actually K6. It is the complete graph, so it has all possible edges joining every vertex here. And in particular, complete graphs are certainly Hamiltonian. I mean, if you have vertex 1, 2, 3, 4 up to n here, then you've got the edge 1 to 2, the edge from 2 to 3, the edge from 3 to 4, and so on. So just going in order will give you a Hamiltonian cycle. Okay, so let's talk about when we have one. It seems to me that this, in first glance, this seems very much like the Euler problem. The Euler was to come up with something and you go over every edge exactly once, and this one we want to go through every vertex exactly once. So it would seem that they are very similar problems, but they're not. Okay, so here is a theorem we're going to take a look at. First off, this is not an if and only if theorem. Okay, this says a simple graph with n number of vertices, n greater than or equal to 3, is Hamiltonian if the sum of the degrees of every pair of non-adjacent vertices is at least n. Well, it's kind of hard to understand what this means, but also notice this gives you a sufficient condition. If you have a simple graph and the degrees of not every pair of non-adjacent vertices add up to n, then it's Hamiltonian. That doesn't give you a necessary condition. Okay, so it's sufficient. If you know certain things are true, then you know it's Hamiltonian, but not every Hamiltonian graph has to have that. Okay, the theorem we had in section 5.1 was a very nice theorem in that the actual proof gave us an algorithm for finding an Euler path. Unfortunately, the proof for theorem 5.3.1 is not a nice proof in the sense that it's not going to give us any idea at all how to find a Hamiltonian cycle in our graph. It's just going to say there has to be one. So it's not satisfying. And what makes it even less satisfying is it's proof by contradiction. So let's set up our contradiction hypothesis here. We're going to suppose that we have a simple graph within at least 3 vertices where the sum of the degrees of every pair of non-adjacent vertices is at least n, and G is not Hamiltonian. So let's suppose the graph meets all our requirements except it isn't Hamiltonian. Okay, what it's going to turn out is we're going to eventually our contradiction is that the vertices, non-adjacent vertices, have to add up to n, their degrees to. Okay, now, if G is not Hamiltonian, it's not a complete graph. It has n number of vertices and it's not a complete graph, but it certainly is a subgraph of a complete graph. I mean, every graph is. Okay, and of course, the complete graph is Hamiltonian. Now, if we start adding edges to G, in other words, make it more and more complete, at some point we'll have a graph that's not Hamiltonian, but when we add one more edge, it becomes Hamiltonian. And it may be that you go up all the way to the very last edge that would make it complete. I don't think that would happen. But certainly there's some finite number of edges we could add to G to make it Hamiltonian graph. Okay. So it's not now. At some point, it would become, so there is some number of edges we can add to this so that the very next edge makes it Hamiltonian. Because at the very next edge, we have a Hamilton cycle. So we've added some edges to G, but not enough to make it Hamilton cycle. Let's call the new graph we get H. Okay. Now, suppose I take a couple of non-adjacent vertices in this new graph. Call them X and Y. Okay. They must satisfy this condition. Well, they satisfied that condition in G. I mean, they weren't adjacent in G, and they satisfied that condition in G, and all we've done is add edges. So they certainly will still satisfy the condition if the degrees were greater than or equal to n to begin with. By adding edges, at worst, you've increased the number of the degrees, so it's still going to be greater than or equal to n. Anyway, if we added an edge from X to Y, okay, remember we're at this point that anytime we add another edge, then we're going to have a Hamilton cycle. Okay, so if we add the edge from X to Y, we get a cycle because that's the way we set things up. So what that means then, if we add the edge, it's going to have a cycle, and it's going to have to then, you would have to include that edge because the cycle didn't exist before I added that edge. So consequently, if we take that edge away, then we actually have a Hamilton path from X to Y. Okay. So I have a Hamilton path from X to Y. Okay. So, whoops. Let's rename these vertices X and Y. Let's call X V1 and Y Vn. There's n number of vertices. And let's call this the Hamilton path we got. The Hamilton path we had when we removed the vertex from, the edge from X to Y. Okay. So something like that starts at X. This used to be X. Okay, remember this was X. And this one is Y. Okay. Now, let's suppose now that V1 is adjacent to one of these guys like V sub n. So I have an edge here. Okay. Can V sub n be adjacent to Vi minus 1 like that? Well, if that was true, then I could go, let's see. Yeah. I could go from V1 to Vi minus 1. Whoops. To V2 to V3 to Vi minus 1. Then I would take this edge to Vn. Then from there I'd go n minus 1 down to Vi and take this edge from Vi to V1. Okay. And what I would have when I did that was I would have a Hamilton cycle without having added that edge. Okay. And that's a contradiction because we have set things up so our new graph is not Hamiltonian, okay, without an additional edge, and I didn't have an additional edge. So what this means is if this first vertex is adjacent to anybody else in the list, then the last vertex can't be adjacent to anything previous to that one. That sounds kind of funny, but this is going to give it to us here. Okay, so let's suppose then that, let's let R be the degree of vertex 1. So that means V1 is adjacent to R number of these vertices. Okay. By what we've shown up here, then Vn cannot be adjacent to R number of the vertices. So So this again, V1 is adjacent to R of the vertices after it, so to speak. Okay. Now what we just showed is that Vn could not then be adjacent to R of the vertices before it. So the degree of V sub n can at most be n minus 1, throwing out the R ones it can't be connected, it can't be adjacent to. Putting this together, the degree of V1 plus the degree of Vn is there's a degree of V1, and this is the most Vn could be. Degree of V1 plus the degree of Vn would have to be less, would have to be less than or equal to n minus 1. But we assumed that the degree of V1 and Vn, x and y, had to be at least n. This is a contradiction. And that then proves our theorem. Okay, so this is a proof by contradiction, so it doesn't really give us any good way to come up with a Hamilton cycle. It just says if under certain situations, we have one. Some corollaries here. This is just kind of a special case. If the degree of each vertex is at least n over 2, then when you add them up, you get something at least n. So that would say for the non-adjacent vertices, that would be true as well. So that would say you'd have a Hamiltonian graph in that case. Loosen the restrictions a little bit. If all you're looking for is a Hamilton path, then if every pair of non-adjacent vertices has the sum of the degrees is at least n minus 1, then you can get a path. Of course, n would give you a cycle, but a path. And the corollary to that would be similar to the corollary above here, that if the sum of the degree, if each vertex has a degree at least n minus 1 over 2, then of course the non-adjacent ones there, they would add up to at least n minus 1, and you'd have a path in that case. Okay, so finding Hamilton paths is not easy. It's basically for us going to be a trial and error process, but they turn out to be very important ideas. And one of the classic problems is talked about in section 5.4, and that's called the traveling salesman problem. The idea here is a road system with sit towns and roads going between them is an example of a graph. And if you're a traveling salesman, you're going to want to visit each town. And the best possible route would be one where you didn't go to each town more than once. So what is the, you might have to, but you'd try not to do that. So the idea is to try to figure out a route that would take you through your territory where you went to each town exactly once. And of course, these might be directed graphs. There might be one-way streets and things like that, one-way roads or whatever. The problem, the traveling salesman problem, has no general solution. It is something that active research is going on, trying to come up with the best way of finding a solution and in what cases you can. If you're interested in graph theory, there's a lot of active work being done in it, and it's something that can be approached. You don't have to study for 5 years in order to understand current research problems. You can understand them very quickly. Okay, that's all we're going to do in section 5.3, and we'll have one more video to look at.